Hi, now we are solving CSIR December 2015 Chemical Sciences. Okay, right. Now just look at the given problem. The biological functions of cytochrome P450 and myoglobin are respectively. So we need to find the correct biological functions of cytochrome P450 and myoglobin from the given four options. Okay, just check them. Oxidation of alkene and oxygen storage, oxygen transport and oxygen storage and electron carrier and oxygen transport. Okay, right. To get the complete information on cytochrome P450 and myoglobin, please check the lectures on biochemistry in your courses. Okay, right. Now just look at the given problem. We need to find the correct statement on cytochrome P450 and myoglobin. Right, here cytochrome P450 act as monooxygenase and it inserts oxygen onto the substrates. Okay, right. Now if we check the first statement, here we have given with oxidation of alkene with respect to cytochrome P450. Yes, here oxidation of alkene is done by cytochrome P450 because it is acting as monooxygenase and it insert oxygen onto the double bond of alkene and result epoxide. So that's why here in the given four statements, the first statement, that is oxidation of alkene for cytochrome P450, is the correct one. Okay, now we need to check for myoglobin. Myoglobin, what is the function of myoglobin? Simply it stores molecular oxygen in our muscles. Okay, so that's why the correct statement for the given problem is A, oxidation of alkene with respect to cytochrome P450 and oxygen storage for myoglobin. Okay, next one, deoxyhemocyanin is heme protein and paramagnetic and colorless and diamagnetic and oxygen transport and paramagnetic and blue colored and diamagnetic. So for this question also you need to check our lessons on biochemistry, okay, in your course. Okay, right. Here hemocyanin has a copper active center and with oxidation state +1. Okay, right. For copper with oxidation state +1, it has D10 electrons. Okay, that's why the d orbital, the subshells of d orbital completely filled, hence there are no unpaired electrons in it, all are paired, hence it is simply act as diamagnetic. And due to the presence of the complete filled d orbital, the electron transitions are not possible, okay, in the presence or in the absence of electric ligand field. So that's why the deoxyhemocyanin is colorless. Okay, so that's why here what is our option? Colorless and diamagnetic is the correct statement about deoxyhemocyanin. Okay, right. Next one, the oxidizing power of chromium, manganese and iron complexes follows the order. So for this kind of questions we need to think logically. Okay, right. Here if you look at the given transition metal complexes, in that all the metal ions, that means chromium, manganese and iron, all of them are in plus, that means all of them having d6 electrons. Okay, and all of them are having oxygen as ligand. So here we need to find oxidizing power. So first thing we need to think to the basics. Okay, we need to think at the level of basic chemistry. Right, here what is oxidizing agent? So we need to think that, then we can give the answer correctly about it. Okay, right. What is oxidizing agent? Simply if a particular species, by accepting electrons from other species, and if it causes oxidation in that species, then we call it as oxidizing agent. Okay, right. Simply here we need to find that oxidizing agent from the given four transition metal complexes. Now so here if we check for electronegativities in the given transition metal complexes, the electronegativities are not greatly altered in the d orbital, that means d transition metals. okay, d black metals, right? That's why here we need to think for other thing, that is size. For example, if we come to the size of d black elements, so the size simply decreases from left to right in the periodic table, we know that, okay, right? That means here the size of chromium is larger than manganese, and which is larger than iron, right? Now whenever the size is less than the nuclear effect or nuclear charge, or effective nuclear charge is more on the particular metal or particular element. What is effective nuclear charge? Simply we know that nucleus has its attraction effect on the electrons which are revolving in the orbitals, right? So whenever the electron and nuclear, that means the radius between the electron or the orbits into the nucleus is less, then the nuclear effects are more on that electrons which revolving in that particular orbits. Or in that kind, what happens? Simply the nucleus is always attracting the electrons, okay, which are revolving on the orbits. That means whenever size is less, the nuclear attractions are more on that particular outer shell orbits, okay. In that kind, it is ready to abstract proton from the outer atmosphere onto that particular element or particular metal, okay. So that's why here whenever the size is less for the particular metal, the effective nuclear charge is more. In that nature, that particular metal act as oxidizing agent. That means it is ready to accept electrons from other because of effective nuclear charge, higher effective nuclear charge on that small sized metal or species, okay, right? So that's why here simply the oxidizing power is opposite to that of size of the particular series here. So in that iron is having greater oxidizing power than manganese, than chromium. So why? Because just considering effective nuclear charge, and that is from size, okay. So that's why here we need to think logically and we need to go to the basics of the chemistry, okay, right? Using crystal field theory, identify from the following complex ions that shows same mu effective, that means magnetic moment, here specially given spin only values. So we have given it cobalt, iridium and iron transition metal complexes. We need to find the correct option, right? First thing, we need to check the number of electrons in that particular complexes. If you see cobalt complex, in that cobalt is in +3 oxidation state, and so it is having d6 electrons, and we need to check for ligand combination or ligand coordination to that cobalt. So here we have fluorine, which is a weak field ligand, so 6 electrons filled equally on T2G and Eg, okay. That's why we have 4 unpaired electrons in it, right? Now we need to check for iridium complex. It is also in +3 oxidation state and it is having d6 electrons in it, okay, right? And here with that means regardless of ligand strength, that means exception here, okay, whenever move down in the transition metal groups, then the effect of ligand on the particular metal, that means transition metal complex, decreases, okay. So that's why regardless of the ligand field strength, we simply the metals in 4D and 5D transition metal complexes always so act as strong field complexes. So that's why 6 electrons after splitting of d orbital, that means in the presence of ligand, then 6 electrons occupy their position in T2G only. In that condition, it result 0, that means 0 unpaired electrons in it, okay. Now we need to check for another iron complex. In that iron in +2 oxidation state, it is also having 6 electrons in its d orbital. In the ligand field strength, in the ligand field, the d orbital splits into 2 energy levels, T2G and Eg. And if you look at the water is weak field ligand, so because it is in 3D, so we need to check for 3D orbital, 3D transition metals, we need to check for ligand strengths, okay. We need not to check for ligand strength in 4D and 5D transition metal complexes, okay. They are always strong, okay, right? Now in that condition, we have 4 unpaired electrons. So just look at, we have in cobalt and iron, that means they have same 4 unpaired electrons. Just recall that spin-only magnetic moment is calculated based on unpaired electrons. Okay, so here these two complexes having a same number of unpaired electrons, that is 4, hence they show same spin magnetic moment. Okay, so this is the answer. Okay, next question, the tungsten and tungsten bond order in the given complex is. So we need to first try to give the total valency electron count for this complex. Okay, so here just check, for tungsten it is simply belongs to chromium transition metal group, and it is having 6 electrons in its d orbital. Okay, that means its valency shell not in d orbital, that is 3d5 for here tungsten chromal tung, so that is 5d5 and 6s1. Okay, that is the correct electron configuration of tungsten here. Then 6 electrons in its valency shell. Now we need to check for ligand, that is C5H5, we have given with neta 5, that means 5 electrons are contributing to the total valency count. So 5 electrons from neta 5 C5H5 and mu Cl, that is bridged chlorine. So for bridged halides we can take 3 electrons in neutral electron count. Okay, and each CO contribute 2 electrons, so here we have given 2 CO, so total 4 electrons. Okay, so we have calculated just on single species here, so but we have given with dimer of it, so 18 electrons. So from this we can get 18, so 18 into 2, because we have given with dimer, so it result 36 electrons. This is total valency electron count in the given tungsten metal complex. Okay, by using this formula, that is total valency electron count is equal to 18x minus 2y. Okay, so which simply result y is equal to 0. So here we consider y as a number of metal bonds in the particular given transition metal complex, and here x is number of metals present in the particular given transition metal complex. Okay, so from that we calculated that y is equal to 0, that means metal bonds are equals to 0 in this complex, right? Next one, the correct statement for manganese oxygen bond lengths in manganese complex. Okay, let's check it. All bonds are equal, and 4 bonds are longer than 2 others, and 2 bonds are longer than 4 bonds, and they are shorter than the manganese oxygen in particular MnO4 minus. Okay, okay, right. Here to give the answer for this problem, we need to check for is there any John-Taylor distortion is possible in the particular metal complex or not. So that is the important thing we need to consider, because whenever John-Taylor distortion is possible in the particular given transition metal complexes, then the equatorial, that means the compression and elongation of axial and equatorial ligands on the particular metal complexes takes place in octahedral transition metal complexes. Okay, so that's why we need to check for John-Taylor distortion is possible or not for the given manganese complex. Okay, right. Now in this complex, manganese in +2 oxidation state, and so it is having d5 electrons. Now we need to check for water, because is it weak or strong. So simply it is weak ligand, hence electrons are filled after splitting of d orbital in the presence of ligand as T2G and Eg. Okay, so we have 5 unpaired electrons in it. Now just observe, in the T2G we have half filled, completely half filled, and in Eg also it is completely half filled. Now for the symmetrical filling of electrons in T2G and Eg, it doesn't result John-Taylor distortion. That means for the given manganese complex there is no John-Taylor distortion, hence so all the manganese oxygen bonds in the particular given manganese complexes must be equal. That means they must have the same radius, okay, in between manganese and oxygen. So that is our option as answer. Okay, next question, among the following species expected to show fluxional behavior or. So just observe, we have given with nickel complex, that is tetrahedral, and IF7, that is pentagonal bipyramidal, and cobalt complex, that is octahedral, and next one iron pentacarbonyl, that is a trigonal bipyramidal. Okay, so we need to check for fluxional behavior, right? So in the given options, IF7, that is pentagonal bipyramidal, just draw its structure pentagonal bipyramidal, and in that the axial fluorines and equatorial fluorines are simply exchange rapidly. That means the spectroscopy doesn't just observe this rapid exchange of equatorial and axial fluorines in the pentagonal bipyramidal IF7. So this kind of rapid exchange of equatorial and axial ligands on particular species are considered as fluxionality. Okay, so fluxionality is observed in IF7. At the same time, FeCO5, that is trigonal bipyramidal structure. Okay, in that axial and equatorial carbonyls simply exchange rapidly, so that is not observed by spectroscopy under normal temperature. This is observed at freezing temperatures. Okay, right. So here these two are the options because they are showing fluxional behavior. Okay, right. Next question, for the reaction of iron, just observe iron complex with trimethyl-phosphine, the main intermediates we have given with NETA5C5H5 ligand and CH3 ligand and 2CO ligands on which are coordinated on iron in the given complex. Okay, right. So first we need to write this complex. So after writing it, just observe here CH3 act as a nucleophile and it simply migrate onto another carbonyl on that particular iron complex. Okay, whenever this CH3 cleaves, it simply it gives a vacate orbital. Okay, and that vacate orbital simply attacked by the neutral nucleophile which is given, that is trimethyl-phosphine, and then we can get the final product as like this. Okay, so what is this and what is the mechanism involving in it? Simply migratory insertion takes place in the given complex by trimethyl-phosphine. So just observe this product in the given options, you can get the answer. Okay, right. Next one, identify the complex ions in sequential order when ferroin is used as indicator in the titration of iron 2 with potassium dichromate. So here phenanthrene 110 phenanthroline, just observe the four options here, we need to find them correctly. Okay, so if you observe the given problem, you can understand that the given titration is simply redox titration. Okay, right. In that iron plus 2 is simply converting to iron plus 3. Okay, whereas potassium dichromate acting as oxidizing agent, that means it simply abstract proton from iron plus 2 of the given iron phenanthrene complex and it produces iron plus 3 phenanthrene complex. Okay, so in that the end point of the particular redox titration is from red to blue. Okay, the color change is red to blue, and here oxidizing agent. Okay, so just check these two pairs of complexes in the given options, you get it. Okay, right. Next question, the structures of xenon difluoride and xenon oxide difluoride respectively are bent tetrahedral, linear, CHEMMaster, linear square planar, bent and CHEMMaster. Okay, first thing, xenon difluoride, we need to write the xenon number of electrons in its valency shell. So it is having 8 valency electrons in it. Now it is having bonding with 2 fluorines, so they are sigma bonds. Okay, right. And then we have 3 unpaired electrons. Okay, each unpaired electron, sorry, we have 3 paired electrons. Okay, so each paired electron is considered as one hybridized orbital. Okay, then we have S, P3 and D. So total sp3d hybridization is possible for xenon difluoride, but it is with 3 lone pair of electrons. Okay, whenever we observe sp3d hybridization with no paired electrons in it, okay, then we simply consider it as trigonal bipyramidal structure. But we have 3 lone pair of electrons in it. Hence just observe in that by just representing 3 lone pairs of in it and 2 bonds with 2 fluorines, we simply have a linear structure for the given xenon difluoride. Okay, right. Now we need to check for xenon O2F2. In that again we need to write 8 valence electrons of xenon, and then we need to take the bonds. Here we have 2 sigma bonds with 2 fluorines, and we have 4 bonds with 2 oxygens, that means 2 sigma bonds and 2 pi bonds, and 1 lone pair of electrons. Okay, so total we have sp3d hybridization possible for this given xenon O2F2, right? And for the normal SF, that means sp3d hybridization, we simply have TBP, that means trigonal bipyramidal structure, but here we have 1 lone pair of electrons, so just write down the 1 lone pair of electrons in it, and it's simply resembling CHEMMaster structure. Okay, right, that means here the correct option is simply linear and CHEMMaster for the given problem. Next question, spin motion of which of the following gives magnetic moment? Electron, proton and neutron. So correct answer is, so just think generally that whenever a particular particle or anything, if it moves on its on itself, when it moves itself, then due to its precision, the magnetic moment generates around it. So that's why, is it proton or is it electron or is it neutron? So there is no question. If any species, okay, so if any species or any particle, if it spins, it generates magnetic moment around it. So that's why here all the given particles, electron, proton, neutron, are correct options. That is, option D is the correct for the given problem. That means spinning of the all these electron, proton, neutron result magnetic moment. Okay, right. Next one, coulometry. Coulometry, it is based on Faraday's law of electrolysis, and it is a type of voltammetry. And 3, it is based on Ohm's law, and it uses ion selective electrode. So just what is coulometry? If we know that, we can give the answer it directly. That is, coulometry determines the amount of matter transformed during an electrolysis reaction by measuring the amount of electricity consumed or produced. Okay, so here simply it is that means coulometry is depending on the electrolysis. Okay, so here the first statement, it is based on coulometry is based on Faraday's law of electrolysis. Okay, so this is the correct answer for the given problem. And if you are interested, visit and join on CHEMMasters.online, and you can also get mobile app CHEMMasters from Google Play Stores, and the courses offered here on CHEMMasters.online or CSIRNet, GATE, JAM, SET, JLDL and IIT Chemistry. One can get the standard concept lectures with the previous year solved problems and standard model problems as assignments on the particular courses to give you the success. Thank you.